Today we're going to start the actual physics. We're going to look at Newton's three laws of motion, and this is pretty much the base material for the entire course, and actually most of the next course. So Newton's three laws are, number one, an object at rest or in motion at constant velocity remains at rest or in motion at constant velocity unless acted on by an external force. Part of this was not new. People had thought, obviously, that things that were at rest stayed at rest unless acted on by an external force. The new idea is that constant velocity could be a natural state of motion. And the reason is friction. If we look at the world around us, we don't generally see things that are in constant motion. If we look up at the planets, that's one example, but there wasn't a really good understanding of the planets back then anyway. What we would see if we go out in space and throw a rock or something like that, it'll keep going forever because there won't be any external frictional force or air resistance slowing it down. If we did that on the Earth, it would very quickly come to a stop because of those two things. The second law says that if we take the vector sum of all the external forces acting on an object, that will tell us the product of mass and acceleration for the object. That means our units of force must be kilograms times meters per second squared, and this comes up so often it has its own name. It's the Newton. We're going to change this law a few times because this isn't exactly what Newton wrote, and as the course goes on, we'll get closer and closer to what the truth really is. Finally, the third law, this is sometimes called the action-reaction law. This says if object A exerts a force on object B will exert an equal and oppositely directed force on A. We can illustrate all three of these laws with one simple example, and that would be kicking a ball. If you don't kick it, the ball will sit there forever. That's the first law. When you do kick it, the force that your foot exerts on the ball is matched by an equal and oppositely directed force from the ball on your foot. You can find this out the hard way. If you kick barefoot with your toes, you'll feel a very large force on your foot. The second law is also in action here because if you try and kick a bowling ball, you'll get a much smaller acceleration than if you try and kick a soccer ball because of the mass difference. For a particular applied force, the larger the mass, the smaller the acceleration. We can look at a more specific mathematical example. If we just imagine dropping a rock of mass m, we're going to continue to ignore air resistance, and the first step here is to make what's called a free body diagram. This is where you draw the physical situation and you have arrows in place representing all forces. This one is pretty simple because we just have a rock and the single force of Earth's gravity pulling on it. The formula for an object's weight is mass times gravity, so that's where we get this mg, and we see that it acts in the negative y direction. Now you have to remember that the second law is a vector equation, so really it means three different equations. Sum of the forces in the x direction equals max, same for the y, same for the z. Now most of the time we'll be working in 2D, so we won't worry about the z equation. But in this case we don't have any forces in the x direction either, so there's nothing interesting to happen there. There won't be an acceleration in either x or z. The only one we care about is sum of the forces in the y direction is may. Our only force is mg. It acts in the negative y direction, so on the left side where we make a list of all these y forces, we have negative mg. On the right we just have m times ay, and of course the masses are the same and they can cancel, so we get that the acceleration in the y direction is negative g. Remember, g itself is positive if you look in your book, which is negative 9.8 meters per second squared. And this isn't anything new to you, but this is where we get this information. Now, if instead of dropping the rock, we have it parked on a table, we have a free body diagram like this, experimentally you know that the rock is not going to accelerate either up or down, so you know that the sum of the forces has to be zero, since ay is zero. And what this means is there must be another force there. And that force that opposes gravity and comes from the table is called the normal force. Normal, not like abnormal and normal, but normal like perpendicular. It's always perpendicular to the surface. Since the acceleration is zero, n minus mg, which is equal to may, is zero, so n equals mg on this flat surface.